Greetings, my name is Matthew, and in this video we're going to talk about the greatest common factor and factoring by grouping. This is the sort of introductory first couple of tools that we really need in order to be able to do successful factoring. And I know from numerous years of experience that this is a topic that a lot of students do not like. So my hope is that I'm going to show you some examples in this video that maybe will even change your mind about factoring. The first little subtopic I want to look at with you is about factoring out the greatest common factor. And remember, even before what's on the screen here, that factors are things that are connected by multiplication. So even if we took the number 6 and we factored it and we wrote it as 2 times 3. 2 and 3 are factors of 6 because they make up the group of stuff that gets multiplied together in order to create the number 6. Another example would be 12, which is equal to 2 times 2 times 3. Is 2 a factor of 12? Yes. Is 3 a factor? Yes. Is 4 a factor of 12? Can the number 4 be multiplied by something to create the number 12? Absolutely. 4 times 3 makes 12. What about 6? Is 6 a factor of 12? Well, can you take 6 and multiply it by something to get 12? The answer is yes. 6 times 2 makes 12. 12 is also a factor of 12 because 12 times 1 makes 12. Realize maybe the most important of everything that I've said so far is that all of those things were being combined or connected using multiplication, and that's what makes them factors. So anytime something is connected to something else, those things are factors. And in problem number 1, we're being asked to factor this expression. And in order to do that, we're going to look for the GCF, the greatest common factor. What does that mean, the greatest common factor? Well, like we did with the number 12, if we break the number 12 up into its smaller components, like 2 times 2 times 3. And then if we looked at another number like, like 18. 18 is 2 times 3 times 3. So that's 18. And 12 we said was 2 times 2 times 3. Do those two factorizations, if you want to call them that, do those two factorizations contain any common factors? Does this list of factors have anything in common with this list of factors? And of course the answer is yes. They each contain one multiple of 2, or one factor of 2, and they each contain one factor of 3. The one on top, the 12, contains 2 factors of 2, but the one on the bottom for 18 doesn't. So we're only looking for what they have in common, the number of instances of those common factors. Now, when we take that and we bring it into our conversation about problem number 1, it gets a little bit more tricky because let's just look at this first term here. How many factors are there just in that first term? Well, 8 is made up of a 2 times a 2 times a 2. So it's got 3 factors of 2 in it. Let's just go ahead and write out some of this. 8 contains 3 factors of 2, so I'm going to write it as 2 to the 3rd power. And it contains 8 factors of x. Remember, x to the 8th power means x times x times x times x. All of those timesings, all of those multiples, attaching one x to the next by multiplication makes them all factors. Then there's a minus sign, and then the next term contains a multiple of 20. And if we take the 20 and we sort of tear it apart, or if we show how it's built or constructed using multiplication, there's a multiple of 2, and then another multiple of 2. So there's a 2 times a 2 times a 5. That makes 20. And then there are 6 multiples of x, or 6 factors of x. And there's a 12, which as we said is made up of 2 multiples of 2 and a multiple of 3. And this term contains 4 factors of x, minus, and then there's another 20. So we've got 2 to the second times 5 times x to the third. Now if we look at all of the factors that are now even more visible, it's almost like we've got X-ray glasses on. We're looking into each one of these terms at all of their little components. Let's start looking for things that they have in common. Let's write down the greatest common factor. So in each one of these terms, I see some multiples of 2. This term contains 3 multiples of 2, 2 multiples of 2, 2 multiples of 2, and 2 multiples of 2. How many multiples of 2 do they have in common? Well, this first term has 3, but this one only has 2. It's almost like if each one of these terms is going to be an equal contributor, well, this first term says, well, I can give 3 factors of 2. And then the next term says, well, he's looking around a little nervously. I can't give 3, but I can give you 2 factors of 2. And the first term right here says, oh, only 2 factors of 2. That's fine. I'll hold on to one of my factors of 2 and I'll just contribute 2 of them. Since that's all you can afford to give, that's fine. And then the next term says, well, I've got 2 factors of 2. I'll chip in both of my factors of 2. And then the fourth term says, hey, I've got 2 factors also. Let's all contribute the same amount with each of us giving what we can afford to give. And it kind of maxes out at each one of those terms contributing 2 factors or multiples of 2. So we can write that as we build our GCF, we can write that as each term contributing not just 1 factor of 2, but 2 factors of 2. Then let's look through and see if there are any other factors that each one of them can give. The x's are pretty obvious. The first term says, well, I can give 8 factors of x, and the next one says, well, I can only give 6. And then the next one says, I've only got 4. And then the last one says, oh, I've only got 3. So the 4 of these terms, they talk to each other and they say, well, again, we don't want to overextend anyone. So, hey, if the fourth term can only afford to give 3 factors of x, let's just all contribute the same amount and give 3 factors of x. So we'll come down here into the GCF and we'll write down that not only are each one of these 4 terms contributing 1 factor of x, but they're all contributing 3 factors of x. And so finally we can clean up this GCF statement and say that 4x to the third is the GCF. Now coming back to this yellow box, when it comes to factoring out the greatest common factor, the GCF, step number 1 is identifying the GCF of all the terms in the polynomial. And we just finished doing that. Step number 2 says to write each term as the product of the GCF and another factor. We could do that and then use the distributive property in reverse, really, to factor out the GCF. I think that we can, in a way, skip number 2 using this sort of an analogy that we've been using so far. Let me try it like this. And if you don't like it, then you can see what you can do with the information in that yellow box. I'm going to take this equal sign and bring it down here. And the first thing I'm going to write down is my GCF, 4x to the third. In fact, let's write it as 2 squared x to the third. Now remember, that's what was contributed by each of the terms. So now, after each one of these 4 terms, 1, 2, 3, 4. Those are the 4 terms. These terms are all separated by minus signs. It could be that we would find terms separated by a plus sign. Terms are always going to be separated by a plus or a minus. And when the first term gives up 2 factors of 2 of its available 3 factors of 2, how many factors of 2 does it have left? Well, it's only got 1. And there it is. And it had 8 factors of x, and it gave away 3 of them. So how many does it have left? It's got 5 factors of x. Now we're going to keep marching our way from left to right, writing down kind of what each term has left over. And in previous and probably subsequent videos, I'll call them leftovers for obvious reasons. So this next term still has its multiple of -1 sort of in there as a minus sign. And then it had 2 factors of 2. It contributed both of them. It also had a factor of 5 in it. And we didn't even talk about this factor of 5 because the first term didn't have it. Since they didn't have them in common, I kind of just breezed right by it. I didn't even mention it, but it's important that I mention it now. Since the multiple of 5 or the factor of 5 isn't common to all of the terms, there's no way we're going to ask all of the terms to contribute a 5 if only some of the terms have a 5. Remember, we want everyone giving equally. So the 5 stays there with that second term. It gave away both of its factors of 2, and it's going to give away 3 of its available 6 factors of x, leaving it with only 3 factors remaining. And then there's a minus sign, and then the third term gave away both of its factors of 2. There is still a factor of 3, however, and of its 4 available factors of x, it gave away 3 of them, so it still has 1 more left for itself. And the fourth term is giving away both of its factors of 2. It's going to keep its factor of 5. So here's the minus sign. There's the multiple of 5. And it had 3 factors of x. It's contributing all of them. It's very generous. And so it has only a factor of 5 remaining in that last term. And so we will close our parentheses. This is a fully factored version of the original typed expression that we saw, except at this point, I would probably change this 2 squared to a 4. Now in your notes, you could go in and erase the 2 squared and put a 4 if you want to, but it might be worth writing it out one more time just so that you can see how the entire story played out as each one of these terms gave the same amount as all of the other terms. And I like to put a box around my final answer. And so there it is. We factored out the GCF. The GCF that we factored out there was a positive 4 times x to the third. Sometimes the GCF is going to be a negative number. Let's look at problem number 4. Another way to, now, in problem number 1, we really took that original expression, this one right here, and we really shredded it. We tore it into all of its tiniest little pieces right there. If that works for you, if you need to go through that kind of a process every time, you may. There are slightly faster ways to do that, and it helps when the expression, the original polynomial, is a bit smaller, like we see in problem number 4. Here, I noticed that 3 is divisible by 3, or contains a factor of 3. The number 12 contains a factor of 3. 3 times 4 would make 12. And 18 contains a factor of 3. 3 times 6 makes 18. But you'll notice that the 3, the leading coefficient, is actually negative. It's a negative 3. Very often that's not desirable. So when I take out my GCF this time, or reverse distribute my GCF, I'm going to factor out a -3. You'll notice that this contains 2 factors of x, 1 factor of x, no factors of x. And since that last term doesn't contain any factors of x, and we like for all of our terms to give equally, no one's going to contribute a factor of x. So when we factor out the multiple of -3, what we have left over is just x squared. And very quickly in your mind, you can imagine distributing and multiplying the -3 times the x squared, and you would certainly get -3x squared. From our next term, when we remove the multiple of 3 times what would make 12, and the answer is 4, except this time it's -3 times what would equal +12. And the answer is -4. And again, imagine distributing -3 times what? Times -4. Negative times a negative makes a positive. The 3 times the 4 makes the 12. There's your +12. Don't forget, though, that that middle term does still have a leftover multiple of x that it's holding on to. And then we jump in and look at the last term. 3 times what equals 18? We said 6. But the 3 is negative, so now it's a question of -3 times +6 or times -6. Which one is it in order to recreate this -18? And the answer is a negative times a positive makes a negative. So this is going to be a +6. Let's double check. -3 times +6. Negative times positive makes negative, which is good because this is a -18, and the 3 times 6 makes the 18, so I think we're good. Very nice. We've factored out a negative greatest common factor. So far, we've been factoring out numbers, we've factored out some variables, we even factored out a variable to a power. That was pretty good. We factored out a negative number. And when I say factoring, you can definitely think of that as reverse distributing. In number 7, this 5 is connected to the x by multiplication, and the x is connected to this kind of large thing right here, this factor of 2x plus 3. The x is connected to the 2x plus 3 by multiplication. So there is still multiplication happening in here, which means the 5 is a factor, and the x is a factor, and in its entirety, the 2x plus 3 is a factor. And then we're subtracting a factor of 2 and another factor of 2x plus 3. When I go to identify my GCF, I'm looking at this term and this term, which are attached, so to speak, by subtraction. This term and this term are connected by addition. So terms can be, think of them as being connected or separated by either a plus or a minus sign. But in problem number 7, in each of those two terms, there's a common factor, a common multiple. And this one's glaringly obvious because it's this giant thing, 2x plus 3 wrapped in parentheses. So the GCF is, you could write equals or is 2x plus 3. And when I reverse distribute that out of this expression, let's write down the GCF first, 2x plus 3. And then after that, in parentheses, let's write down the leftovers. After this 2x plus 3 is gone, what's left? A 5x. And after this 2x plus 3 is gone, what do we have left? Just the -2 or -2. And this is as far as you can go. There are no other common factors. And interesting, this looks like a binomial times a binomial. This looks like the kind of thing that you would FOIL. And it is the kind of a thing that you would FOIL. But the reverse of the foiling process, the reverse of the distributing process, has this task of factoring out a binomial as part of it. So I'm showing you little bits and pieces of a larger picture, and I promise you we will be looking at the larger picture and see how all of these fit in there. So we factored out a binomial as a common factor and this note. This little feature, factoring feature, is something that pops up every once in a while. Not all that often, but every once in a while. Remember that 2 plus 3 is equal to 5, and 3 plus 2 is also equal to 5. So when you're working with addition, you can sort of swap the numbers around on either side of the plus sign. However, 2 minus 3 is equal to -1, which does not equal 3 minus 2. So you cannot take two numbers and flip them around on either side of a minus sign. However, this says b minus a and this says a minus b. How did we manage that? The answer is we factored out a multiple of -1. We reverse distributed a negative. I don't want to go into the process of it. It's not a long process, but just realize that if you factor out a negative from the positive b, it becomes negative. And if you take a negative away from the negative a, it becomes positive. And sure enough, there's the positive a and the negative b, and there's that negative that you factored out of the expression. All right, factoring by grouping. I'm going to use probably most of this space on the right-hand side in order to solve number 10. And in fact, number 10, let's actually do number 11. It's just a little less complicated looking. I don't want this problem, this example that I do for you, to be visually overwhelming, but the process we're going to do in number 11 is the same process you could use in numbers 10 or 13. So let's try number 11. I have x to the third minus 5x squared plus 4x minus 20. And here's the very first thing that I'm going to do when I factor by grouping. I'm going to do the grouping. Okay, here's what the grouping looks like. I'm going to put, I call it an under bracket, and I'm going to put it under those first two terms. Sorry. I'm looking at my levels, and I just wanted to turn the gain down a little bit. It looked like I was maybe maxing out the microphone. Okay, so there we go. I think that's a bit better. So I put an under bracket under my first two terms, and then I'm going to put another under bracket, which is not a technical term. I don't even know anybody else who says under bracket. But there's an under bracket under the second two terms. And notice that my second under bracket includes this plus sign. Not so important when it's a plus sign, but when it's a minus sign, it's very important that you include it in the second group. Okay? Now, so you should be taking notes on these notes. Step number 1 is the grouping using under brackets. Include second sign, second operation in the second group, or you can call it the middle operation or the middle sign. That plus sign needs to go in the second group. All right, so you've got your under brackets, you've under bracketed correctly. The next step is to factor out the GCF from the first group, and then we're going to factor out the GCF from the second group. In the first group, both terms contain two factors of x. In other words, x squared. So I'm going to put my equal sign. I'm going to reverse distribute out an x squared. I'm going to write down my leftovers. That's an x. X squared times x would make x to the third. And my next leftover is a minus 5. X squared times minus 5 would make minus 5x squared. Perfect, there it is. So I know I'm doing this right. Every time I factor something out, I'm doing the quick little bit of distribution in order to check, make sure I did it all right. So that's factoring out the GCF from the first two terms. Now what's the GCF in the second group? Both of those terms contain a multiple of 4. and a positive 4 at that. So I'm going to write down my positive 4, and then here come my leftovers. 4 times x would equal 4x, and 4 times negative 5 would equal negative 20. And wouldn't you know it, I've got a term here and a term here, and each one of those two terms contains a common factor. It's the really glaringly obvious one again. It's the one that's in parentheses. So we're going to do what we did in the previous exercise, is factor out a binomial from these two terms. Now make sure you write down a note that says that that's what we're doing. Okay, I don't want you to just be looking at a string of math. I want you to be over here on the right hand side. If you've got room on your paper, you should be putting notes down over here in English or whatever language you prefer about how it is that we're going from line to line. So in order to go from this line down to this line, what are we going to do? We're going to factor out the GCF from these two terms. The GCF is the x minus 5. The leftovers are the x squared and the positive 4. After this term contributes the x minus 5 and this second term contributes the x minus 5, what's left? The leftovers, an x squared and a positive 4. There they are. Fantastic. We did it. We performed factoring by grouping, and as a result, we got a binomial times a binomial, the kind of thing that can eventually be FOILed. And in fact, if you went through the process of foiling this answer, FOIL, you should, and you better, get your original expression again. Let's see. Do I have any other examples in this section that I'd like to show you? I do not. So we're going to stop at factoring by grouping in this video, and if you'd like to join me in the next video, we're going to take factoring to the next level. I'm going to, I believe it's the next video where I'm going to talk to you about the AC method, and that as an integral part of the AC method, we need to be good at factoring by grouping. And to be good at factoring by grouping, we had to be good at factoring out a binomial. And in order to create those binomials, we needed to be good at factoring out sometimes a negative, but definitely being able to factor out a GCF. This was a really great section, the way that these little tools built into something more complex. And in the next video, we'll take it to the next level with factoring using the AC method. See you there. Thanks.